Okay, I'd like to first thank the organizer for organizing this very nice workshop. And today I'm going to introduce our software CIGALE, and I'm speaking on the behalf of the CIGALE collaboration. First, what is CIGALE? CIGALE is the abbreviation for Code Investigating Galaxy Emission. It is an open source software for SED fitting multi-wavelengths. And the CIGALE has many good features. For example, it's very physical. It can build multi-component physical models, and all the models are based energy conservation. Also, CIGALE is very efficient, and for most of the runs, even for like thousands of galaxies, it can finish the run within a few hours for most cases. Also, it's very easy to use as it's written in modern Python 3, and the configuration files are self-explanatory, and also they are very nice plotting tools. You can plot the nice figures here, and it's very easy to use. But CIGALE cannot deal with the X-ray data previously, and the X-ray data, as we know, it's very important because it can reveal AGN activity and very sensitively reveal AGN activity. And so we started the project called XCIGALE. And we aim to develop the X-ray module. Now it has been formally published. And in this new X-ray module, we can allow CIGALE to account for both AGN and galaxy X-ray emission. And for galaxy, it includes both hot gas and binary. And although we know for most cases AGN is dominant, but for deep X-ray surveys like Chandra Deep Field South, you can see many galaxy X-ray emission as well. And for the future Athena, you will find even more galaxy X-ray. We also introduce other improvements like Clumpy AGN torus model, also polar dust obscuration for type 1 AGNs. So first, how do we introduce the X-ray module? And we need to connect the X-ray to other wavelengths. For the AGNs, we know there is a very good relation between the X-ray luminosity and the UV luminosity, which people often use the 2 keV and 2500 angstrom luminosity. And this relation covers like at least 3 orders of magnitude, and with a very small scatter of only a factor of about 2. So we apply this relation to X-scale to build the X-ray module so that the AGN X-ray is connected to the UV optical emission. For the galaxy emission, we adopt the Fraggle's 2013 model, which is a verified observation. And in this model, we can build the galaxy X-ray emission as a function of stellar mass, star formation rate, metallicity, and stellar age. And this is how we build the X-ray module. And here is an example to show why the X-ray module is useful. Here is the same source. On the left-hand side plot, we use the X-ray data to fit, but on the right-hand side, we do not use the X-ray data when doing the SED fitting. You can see on the right-hand side, there is a very significant AGN component in infrared, and the best fit AGN bolometric luminosity is 45, very high. Yeah, but if you just plot the expected X-ray and plot the observed data points, you will find the expected X-ray emission much higher than observed. And then you add the X-ray data and fit all things together, then the code knows the bolometric luminosity should not be that high. And then it can give a more reasonable value if you add the X-ray data, because it tells you the intrinsic AGN X-ray emission. In this way, we can avoid an overestimation of the AGN luminosity for this source. So that shows how useful the X-ray is for the AGN. But for most of the optical infrared sources, X-ray survey cannot detect them. In fact, only like a few percent of the optical infrared sources can be detected in X-ray surveys. And for the rest of the sources, there is only upper limit available. But fortunately, XScale can allow the upper limit analysis to constrain the AGN component. This means that if you have a deeper X-ray survey, you will have a tighter constraint. For example, here we compare the frac AGN, which is the AGN fractional luminosity in terms of total infrared. And if you apply the current changer upper limits, you'll find sometimes it's a little bit useful, but for most cases, it's only affect things a little bit. But if you replace the changer upper limit with the Athena upper limits, you can rule out the AGN component for almost all of the sources. So in the future, if you have Athena data, it will be very promising that you can know whether there is an AGN for each of the infrared select sources for the Akari NEP or test case. So XScale also introduced a new Clumpy torus model called Skelter. That's because in previous CIGALE only have the smooth torus model from Freitas model, and the smooth model is unphysical because it requires a temperature of millions of Kelvin per dust, which is apparently too high. And in the Clumpy torus model, on the other hand, most of the dust is in the clump and they rotate around the central engine. So XScale, we also add the polar dust extinction for type 1 AGN. That's because in the previous scale version, there was only a torus extinction for type 2 AGN, but for type 1 AGN, there is no extinction at all. But recently observation found that in fact in the polar region, there are lots of dust emission. And also in the optical UV SED, we see many extinctions for type 1 AGN. So we allow users to add a polar dust component in the polar direction for type 1 AGNs. And actually, we have a dedicated paper to test the polar dust. We found that about 30% of the type 1 AGNs have a very significant polar dust extinction. So it's quite important to introduce the polar dust. Recently, we want to further update CIGALE, and that's because the previous XScale or CIGALE only have galaxy radio emission, and it does not deal with the AGN radio emission. And so we want to extend the model further to the radio wavelengths. So we will formally release the version as the CIGALE version 2022. And in the radio emission, we model the AGN as two parameters. One is R AGN, which controls the normalization of the AGNs. The other is alpha AGN, which controls the slopes of the radio emission, where we assume that it's a parallel emission. And we also introduce other new features such as X-ray anisotropy. We want the X-ray depend on the viewing angles, which there are many observational evidence for that. We also allow the user to adjust the AGN continuous slope, because we know that AGN differs from AGN and they have different UV optical slopes. We also adopt a more flexible X-ray binary recipe. And for now, we think that the new version of CIGALE will be the only code in the world that can simultaneously fit radio to X-ray data, including both AGN and galaxy components. So we have tested our new CIGALE version on the Cosmos data, and now where there is a very deep radio data as well as other multi-wavelength data from X-ray to far infrared. And you can find here on the left is fit without the radio AGN component. You can see that many of the model radio flux is very low compared to the observed radio flux. And that's very strongly indicates you really need a radio AGN component. So after adding the radio component, the model flux agree with the observed radio flux very well. Actually, from statistical analysis, we found about half of the sources have a significant AGN component. So here I want to show you with more SEDs, and for the AGNs, you can find from the SED you can find that there are really a diversified AGN population. For example, on the left-hand side, people may call it radio galaxies because it's only the AGN component is only strong in the radio. It's very weak in optic infrared or X-ray. And on the right-hand side, on the other hand, is people will call it radio loud X-ray AGN because it's not only detecting radio but also very strong in the X-ray, but very weak in the optical infrared. Here are two more examples. On the left-hand side is the so-called radio quiet X-ray AGN. The radio is dominated by the galaxies, and it's only strong in the X-ray. On the right-hand side is the sort of a radio quiet mid-infrared AGN, just because it's very weak in the radio or X-ray, but has very strong feature in the optical infrared. So I want to here I just show these examples. Just want to show you that it's very important to have a really multi-wavelength censoring of the AGN activity from X-ray to radio. Otherwise, you probably will miss some of the AGNs. You really need multi-wavelength data, which is challenging. But the future is really bright. We will soon have many wide, deep multi-wavelength surveys from X-ray to radio. In the X-ray regime, we will have Rosetta will provide all sky survey. Athena will give you many deep X-ray surveys. In the optical, we will have Xuntian or CSST. Will provide a UV optical survey as well as a Rubin Observatory for the southern sky optical survey. In the near infrared, we have Euclid, also mid infrared, GWST for the infrared surveys. In the radio, it's more exciting. We'll have LOFAR, which is ongoing. We'll survey the entire northern sky. And the SKA in the far future will give you both wide and deep surveys. And what I want to say here is that all these data can be used by SEGALE, and using all these multi-wavelength data, we can do cutting-edge AGN galaxy science. As I showed in the previous slide, that the AGN is really tricky to detect all of them. You really need all the multi-wavelength data, and to detect them in the future, we can use all these multi-wavelength together and in SEGALE, and to do really good science. And here is my summarized slides. And first, SEGALE is the most powerful SED fitting code in the world that can deal with radio to X-ray data simultaneous, and all the multi-wavelength data are simultaneously connected together, and including both AGN and galaxy components. So if you have a multi-wavelength actual galaxy surveys, I strongly recommend to use our code. And from our test of Cosmos data, where we have good data from X-ray to radio, we found there is a very diversified AGN population. And those population highlights the importance of multi-wavelength sensoring. And in the future, SEGALE can be applied to big survey data from X-ray to radio, and including Athena, CSST, Euclid, or LOFAR. All this multi-wavelength data can be applied to SEGALE and extract the physical parameters and do cutting-edge sciences. And I would strongly recommend to check out our website for the latest release and developing versions, also for the discussion forum, and you can ask questions and discuss with the entire SEGALE community, and just log into the SEGALE website, and you can find everything you need about SEGALE. I think that's all I want to talk about. I'm happy to take any questions.
Thanks. We have a question from Jérôme.
Yes, in your model of AGN, you're putting dust in polar dust, but there is no dust in the.
Here.
Yes. There is no dust in the torus?
Oh yes, there is dust in torus. There are a lot of dust in torus. Here is the dust torus model. You can see each of the clumps are a lot of dust clumps. And in fact, if your viewing angle is type 2, if you view across the torus, all the UV optical emission are obscured. Yeah, the torus has more dust than the polar region actually. In the polar region, it's just a mild amount of dust, but in the torus, there are tons of dust.
No more questions from the room? No? Just last one from me. When you say that you put dust, what kind of dust do you put, and does it really matter what you put? I mean, for the temperature or this kind of things.
Oh, that's a good question. Actually, for polar dust, we don't. We allow the user to choose like 3 extinction curves, and including SMC, also the one AGN, one quasar extinction curve, and one Milky Way extinction curve. So people can choose which extinction curve they like. And then for the dust re-emission, we model it as a black body with a single temperature black body. Although it's sort of oversimplified, but it's a first step to keep the energy balanced. And by the way, user can set the temperature of the dust. It really depends on the physical location of the dust. We don't specifically modify it, but the user can set a temperature to fit their SEDs.
Okay, thank you.
Yeah, thank you.